In this video, we'll discuss about Einstein's A-B coefficients. So, question will come like this: derive Einstein's A and B coefficients. In Einstein's A and B coefficients, you have three coefficients. One is your A, another one is your B12, and the third one is your B21. Your A is called your constant, which is related to spontaneous emission, and the constant B12, you have in B you have two constants, B12 and B21. B12 is basically related to absorption coefficient in absorption, and B21 it is a constant which is in related to stimulated emission. And we have discussed in the previous video in detail about absorption, the spontaneous emission and stimulated emission. The phenomena of stimulated emission was first predicted by Einstein in 1917 purely from thermodynamical consideration. Now we will discuss about absorption. Absorption first. What happens in absorption? Suppose you have two states of energy of the atoms. One is your E1, which is at lower energy state, another state of energy G2 at higher energy state. And if you incident photon having energy hf, h is the Planck's constant, f is the frequency of radiation, then what happens? The atom in this state E1, it will absorb the incident energy of this incident photon and go to the higher energy state, that is the state E2, and this process is called absorption process. And mathematically you can write the rate of absorption is directly proportional to N1. Here N1 is the number of atoms per unit volume which at a given time are all at a energy level E1. So mathematically you can write the rate of absorption is directly proportional to N1. So the rate of absorption will be equal to a constant into N1, and this constant W12 can be written as the product of two constants. One is your B12 and another one is your phi. And what is B12? B12 is the cross section of absorption which depends upon the type of transition. What type of transition we are doing in the experiment, that depends upon the B12. B12 depends upon this type of transition and its cross section of the absorption. And what is phi? Phi is the flux density of photon of the incident wave, because we provide photon or we incident photon on the material for the transition from the state E1 to E2. So you can write the rate of transition in absorption, or the rate of absorption is equal to B12 N1 into phi. So I have told you in Einstein's coefficients you have three coefficients. So here B12 is one coefficient which is basically related to absorption. Next is your spontaneous emission. As we have discussed about spontaneous emission in the previous video, in spontaneous emission the atomic system is in the higher energy state. As shown in this figure, the atomic system is in higher energy state, and after a time, let us say tau, the atomic system moves of its own accord to the state of lower energy state. That means the atomic system changes from E2 to E1. Then what will be the difference in energy? The difference in energy is equal to E2 minus E1, and the difference in energy E2 minus E1 is equal to HF. This is the energy of the radiation of the photon. So here radiation takes place, radiation of photon takes place of its own accord, and we call this process is spontaneous emission. And suppose in this spontaneous emission, the rate at which the decay of atom takes place from energy state, higher energy state E2 to the lower energy state E1, and that is equal to the derivative of N2 with respect to T. So this is the rate of decay, the rate of decay of the atoms. So that will be proportional to minus N2. Here N2 is a constant which is called the number of, here N2 is called the number of atoms per unit volume which at a given time are all at a energy level E2. All the atoms that is equal to the number of atoms which is equal to N2, and they have at the same energy level. And this is basically we measure in terms of number of atoms per unit volume. So this will be equal if a constant is multiplied. So the rate of atom that decay spontaneously, that will be equal to minus of A into N2. Here A is the Einstein's constant. As I have told you in the beginning, we have three constants, A, B12 and B21, and here A is the Einstein's constant which depends upon the type of transition. Now we will discuss about stimulated emission. What is stimulated emission? We have discussed in detail about stimulated emission in the previous video. What happens in stimulated emission? The atomic system is in its upper energy level, that is here at E2. And suppose a photon of energy hf interacts with this system, then the system is driven down to its lower energy state. You see, the system will be driven down to the lower energy state E1. Now there are two photons. One previously we have given incident a photon hf, and another photon due to the change of energy of the atom from higher energy state E2 to the energy state E1. So you have two photons. So this the system is driven down up to its lower energy level, and there are two photons. So where only one excited before, you see here there is one excited before. So this process is called stimulated emission. And suppose the rate of stimulated emission from the state E2 to the state E1 is given by derivative of N2 with respect to T stimulated, and that is proportional to minus of N2. And here N2, as we have discussed in the spontaneous emission, N2 is the number of atoms per unit volume which at a given time are all at the energy level E2. Then what will be the rate of emission, stimulated emission? That will be equal to a constant multiplied by N2. If you multiply a constant W21 is equal to B21 into 5. Okay, W21 is equal to B21 into 5. So what will be the rate of emission? W21 into 5 into N2, is not it? Into N2. So the rate of stimulated emission will be equal to minus B21 N2 into 5. So here what is B21? B21 is your cross section of the stimulated emission, which depends upon the characteristic of the particular transition, and phi is the flux density of photon of incident wave. So you have three factors, one from absorption and another two factors. This is from the spontaneous emission, and this factor is from the stimulated emission. In thermal equilibrium, what happens? The N1 B12 phi will be equal to N2 A plus N2 B21 into phi. So if you rearrange the terms, then what will be phi? you take phi this side, then you will take common n1 b12 minus n2 b21, and this side you have n2a. So phi will be equal to, if you take if you divide n2 here in the denominator, and this factor will be equal to n1 by n2 b12, and this factor will be equal to 1. So phi will be equal to a divided by n1 by n2 into b12 minus b21. And according to Boltzmann law at thermal equilibrium, we have deduced it in the previous video, that is the population inversion. In the video population inversion, we have deduced it, that is n2 divided by n1. n2 is the number of atoms in the higher energy state, n1 is the number of atoms in the lower energy state, and this is called the Boltzmann's law for thermal equilibrium. So n2 is equal to n1 into e to the power minus e2 minus e1 divided by kt. So n1 by n2 will be equal to e to the power e2 minus e1 divided by kt. So you now compare equation 5 and 6. So if you compare, you put these values, put this value of n1 divided by n2 here, then what will be phi? Phi will be equal to a divided by, if you put n1 by n2 here, e to the power e2 minus e1 divided by kt into b12 minus b21, then what will be your answer? Also phi will be equal to this much, a divided by e to the power e2 minus e1 by kt into b12 minus b21. And according to Planck's law of radiation, we know phi equal to the energy of radiation, that is the flux density of photon, phi equal to 8 pi hfq divided by cq into 1 divided by e to the power hf divided by kt minus 1, where h is the Planck's constant, f is the frequency of radiation, c is the velocity of the photon, and k is the Boltzmann constant, t is the absolute temperature. So if you compare these two equations 7 and 8, and before comparison you put e2 minus e1 is equal to hf, then you can compare. So e2 minus e1 is equal to hf, you put the value of hf here, then phi will be equal to here a divided by e to the power hf by kt b12 minus b21. Now what you do, you write here, you take common b12, in the denominator you take common b12. So this factor will be equal to e to the power hc by kt, so minus b21 divided by b12, because you have taken b12 common. Now you can compare, you see equation 8 and 9, they are similar type. 1 divided by e to the power hf by kt, here also 1 divided by e to the power hf by kt, and here minus 1, and here b21 divided by b12, this will be equal to 1, this factor will be equal to 1, and this factor will be equal to this factor. So if you compare these two equations 8 and 9, you will get this value b21 by b12, they are equal, b12 will be equal to b21. And if you compare this with this, you see a divided by b12 will be equal to h by 8 by hfq divided by cq. So a divided by b12 is equal to 8 by hfq divided by cq. So a will be equal to b12 into 8 by hfq divided by cq. So you can write, since b12 is equal to b21, you can put a12 or b12 or b21. So you will get the two expression, one for 12 b12, another for b21, the equation 11 and equation 12. So you have three equations now relating to a and b12 and b21. In equation 10 you see you have a relation between b12 and b21. So these three equations, equation 10, equation 11 and equation 12, are called Einstein's equation. Remember, these equations B12 is equal to B21, another A equal to B12 8 by H FQ divided by CQ, another A equal to B21 8 by H FQ divided by CQ. These three equations 10, 11 and 12, they are called Einstein's equation. And A, B12 and B21, they are called the Einstein's coefficients, and these coefficients are related to one another. You see how these coefficients are related to one another. So this is a brief description about Einstein's coefficients. And a long question will come in this chapter, that is derive the Einstein's A and B coefficients, and you have to derive these three coefficients B12, B21 and A.